Good morning. Hopefully this meeting won't be as hard to join as yesterday's was. I'm going to kind of give it a second and see if anyone's able to hop on here. All right, I'm going to go ahead and start. And let's see. We are starting on page 498. And I'm going to try to kind of breeze through the rest of the chapter today and tomorrow and give you your practice test for homework. Excuse me. So we're just going to kind of hit the highlights on module 14, and it won't be on your test for next week. So let's go ahead and start on page 498 at the top. They are gonna go ahead and refer back to that first equation that we talked about yesterday. It's equation 14.1 on page 493, and it's an equation for reaction rate. And that equation is only good for an average over the time interval for which the change in time was calculated. So if we calculated the reaction rate after 30 seconds, then that R from equation 14.1 is only good at the 30-second mark. Why is that? What is happening to the concentrations of the reactants as time goes on? Well, our experiment that we looked at yesterday online showed that the reaction rate gets slower as the concentrations get smaller. So we should expect that R, the reaction rate, at 45 seconds would be smaller than the R calculated at 30 seconds because things are slowing down as the chemical reaction goes on. So is there a way to figure out what the rate would be at any time during a chemical reaction? The answer is yes. These mathematical equations are based on the concentrations of the reactants. Since the concentration of the reactants has a profound influence on the rate. So this equation that we're going to use next, if you see on page 498, there is a generic chemical equation that they're going to use to represent all chemical reactions, and it's lowercase a, capital A, plus lowercase b, capital B produces lowercase c, capital C, plus lowercase d, capital D. This might be weird, but it's just to kind of help us figure out how to use this next equation that they're going to give us. So this represents a general chemical equation that has reactants capital A and capital B, which react to form the products capital C and capital D. And the lowercase letters, the lowercase a, b, c, d, those just represent the stoichiometric coefficients. So the coefficients that are normally in front of each substance, that's what those lowercase letters are representing there. And with that generic equation, we're going to then plug that into equation 14.2. And this is called the rate equation. And the rate equation is capital R equals K, the concentration of reactant A, to an exponent of X, the concentration of reactant B with an exponent of Y. And this might sound confusing, but let's kind of break it down. R represents the rate of the chemical reaction, which is what we're trying to measure. A in the brackets represents the concentration of reactant A. B in the brackets stands for the concentration of reactant B, and K is called the rate constant for the chemical reaction. The letters X and Y represent exponents for the concentrations of the reactants. Now, this probably sounds really confusing, but don't worry, because I promise this is actually one of the easier ones, I think. Okay, so let's see. First, let's look at the concentration terms. So what happens to the reaction rate when the concentration of either A or B increases? Well, based on the equation, because they're being multiplied, we would expect R to increase if the concentrations are increasing. And that makes sense because, as we said yesterday, higher concentration equals a faster reaction rate. Okay, so when reactant concentration increases, the rate increases as well. And previously in the equation we talked about yesterday, we used a negative sign to indicate the loss of reactants over time. But the rate equation that we're using right now addresses the overall speed of the reaction, so we don't need a negative sign when we're using the reactants. So no negative sign here. Let's see. So also we want to know how much it increases, not just that it increases. So for example, if we double the concentration of a reactant, will the reaction rate double? Will it triple? Will it quadruple? So that's kind of the question that we're looking to answer when we use this equation. How quickly is it going to increase? That's where the exponents are coming in. All right. They allow us to determine exactly how much reaction rate changes when the concentration changes. And you'll kind of see that when we do an example. X is called the order of the chemical reaction with respect to reactant A, while Y is the order of the reaction with respect to reactant B. And if we add the two together, X plus Y, I'm at the top of page 499, by the way, we get the overall order of the chemical reaction. And we'll kind of talk about that later on in the module. Finally, let's talk about K. K represents a number that's unique for each chemical reaction. Its value is independent of the concentration of any reactant. That's why it's called the rate constant. The important thing to remember is that there's only one way to determine X, Y, and K. And the way that you determine those is by experiment. We're not going to do the experiments. We're just going to observe some results of experiments that other people have done. So let's see. Let's go to example 14.1 so we can kind of just see how this equation is going to look. Write the rate equation for the following chemical reaction, and there's N2 plus 3H2 produces 2NH3. According to equation 14.2, we get the rate equation by just taking the concentration of each reactant and raising it to the power of X or Y. So you'll see there R equals K times, and then the concentration of your first reactant, N2, raised to the X power, and then the concentration of your second reactant, H2, raised to the Y power. This wasn't very hard. We're just plugging in what we have. We don't have X, Y, or K because there's no experiment here to observe. But that is the rate reaction, even though it tells us nothing. They're just kind of showing you how you're going to plug that in. All right, so now let's talk about how we're going to use experiments to actually do the equation. All right, so once we have that, it allows us to predict the rate of the chemical reaction regardless of the concentrations of either reactant. So once we know the formula, we can plug in any concentrations and it's going to give us the rate at that concentration. So this, let's see. There is a standard experimental technique that you can perform on any chemical reaction that allows you to calculate the values of K, X, and Y. The first thing that you need to do is run the reaction, then measure its rate, and you need pretty high-tech equipment to do that. So as a result, you can't really do that in high school chemistry. So like I said, we're going to learn how to analyze the data rather than actually measuring it in the rate equation. So go ahead and flip your page to page 500, and there's an example here. It's really long. Don't get intimidated. We'll go through it together. So example 14.2 on page 500. A chemist runs an experiment designed to determine the rate equation for the following reaction. 2ICl plus H2 produces I2 plus 2HCl. To do this, she runs the reaction 3 times, varying the concentration of the reactants. So she put a table there. The first column is showing you which trial. So she did 3 trials, trial 1, trial 2, trial 3. The next column is telling you the concentration of the initial concentration of ICl, the first reactant. So that's iodine and chlorine, right? And the next column is giving you the initial concentration, so the starting concentration of H2, which is your other reactant. And the last column is telling you the instantaneous rate the chemist measured when she mixed the reactants together. So don't worry about that word instantaneous yet. We'll kind of talk about that later. For now, just know that this represents the experimentally measured rate of the chemical reaction. And then you'll see the unit there, M divided by S for the rate, and that's molarity per second. So that just tells us the unit there. Okay, now let's kind of start to solve the problem. So first, we're going to write the rate equation to the best of our ability, just like we did on the last page. And it should look something like, they're 3/4 of the way down on page 500. R equals K, because we don't know K yet, the concentration of your first reactant, ICL, to the X power, and the concentration of your second reactant, H2, to the Y power. Okay, again, we don't know K, X, and Y yet, so let's look at the data and see if we can figure them out, because there is data for us here from the experiment. All right, so at first we'll see that she started out with equal concentrations of both reactants for her first trial. The next row says that the second time she ran the experiment, you'll see that ICL, she's still kept at a 0.25 concentration, but the H2 has been doubled. It went from 0.25 to 0.5 for trial 2. So what we can conclude from that is that any change in the reaction rate is going to be based solely on that change in concentration of the H2, because that's the only one that was doubled. The ICL is the same. So anything that happens between the two is going to be as a result of the concentration of the H2. So between trial 1 and trial 2, the concentration of H2 doubled, and what happened to the rate? Okay, so it went from 0.0102 to 0.0204. So when the concentration of H2 was doubled, the reaction rate doubled. So this is enough to tell us what we need to get for Y, because Y was your exponent for H2. All right, so I'm at the top of 501. If the concentration of H2 doubled and the rate also doubled, that tells us that Y equals 1, because if doubling the concentration doubles the rate of reaction, that means they're linearly proportional to one another, which means that Y equals 1. Hopefully you'll understand this a little bit more in a minute. So next, let's look at what happened with the ICL and see if we can kind of figure out the rate of reaction for X. I mean, not the rate of reaction, but if we can figure out X. So to do this, we need to look at the two trials that keep the concentration of H2 the same, but change the concentration of ICL. So it looks like we can use number 2 and 3. We're going to use 2 and 3 because in trial 2, you have a concentration in ICL of 0.25, and in trial 3, you have 0.5. So from 2 to 3, she doubled it. Now, you'll notice that H2 stayed 0.5 for both of those trials. So any change in the rate is going to be based solely on the change in concentration of the ICL. So we're looking at trials 2 and 3. And what we're going to notice is that when we double the concentration, the instantaneous rate of reaction went from 0.0204 to 0.0408. Again, just like with the first reactant, it doubled. So that means that your your X value is going to be 1 as well. Okay, so we have X, we have Y, now all we need is K. All right, so we need to choose any one of the 3 trials to plug into our equation to solve for K, right? Let me do this on the screen for you to kind of help you out, hopefully. Even though you have it in your book, sometimes it helps to see it. Okay, so what we have to begin with is R equals K, the concentration of ICL, and the exponent is just 1, so it's just going to stay the same because anything to the first power is just the same. So now our second one was H2. Okay, now I'm going to plug in for any of the 3 trials. All right, so it looks like for them, they use the first trial. So we're just going to plug in the values for the first trial. So R is that last column, the reaction rate. So we're going to plug in the reaction rate for the first trial equals, whoops, sorry, I don't know why there's an N, equals K. We don't know K. And now let's do the concentration of ICL, which is 0.25. Sorry. And then the concentration of H2, which is also 0.25. Okay, now we're just solving for K. So what I need to do is divide this side by 0.25 times 0.25 and divide this side by 0.25 times 0.25 so that these will cancel and K will be all by itself. So what it's going to look like is this: 0.0102 divided by 0.25 times 0.25 equals K. You see how I moved that over there? Hopefully you do. No one's here to respond, but I hope you see that. Okay, and then you're just going to plug it in your calculator. So once you do that, and don't forget your units. I forgot to plug those in. So this is molarity per second. And the concentrations are just molarity. So as you'll see, we have one molarity canceling because there's one molarity on the top. So all we have left unit-wise is seconds times molarity on the bottom. That's going to be our unit. So we plug it in the calculator and we get 0.16. And like I said, that was 1 over molarity times seconds. Weird unit, but that's what we're left with because this molarity canceled with this molarity, and all you're left with is a second on the bottom here and a molarity on the bottom here. So that's what you have. All right, so since K is going to be constant, let me go back here, regardless of the concentration of the reactants, we can use this for any trial. So let's see. We talked about the unit. Let's go to page 502. All right, now that we have the final rate equation, we can predict the rate of the chemical reaction for any concentration of reactants. That's what I was trying to tell you guys. So if the chemist wanted to run a fourth trial, we could determine the rate of reaction under those conditions. Say they wanted to use a concentration of 1 molarity for ICL and 0.75 molarity for H2, you could just plug it in your rate equation. So your final rate equation is going to look like this. Hopefully I can. Okay, your final rate equation, we just plug in our values. Is going to be R equals, we know our K there is 0.16. And then we put our unit for that. So that's K, and then the concentration of ICL. Remember, X is just 1, so we don't need an exponent, and the concentration of H2, and remember that exponent was 1 as well. So this is your final reaction rate equation, and like they were saying, if you wanted to run another trial with different concentrations, you just plug it in, and that will give you your reaction rate for those concentrations. So you can use that for any trial that you would run. And let's see, so that means once we have that figured out, we can use that to determine how fast the reaction goes at any concentration of reactants. So it's very useful. And the first thing that we need to do in analyzing an experiment such as the one given to us is to look at the data. So that table that they give you is so important. Look at the data. So we do that first. Then we say any difference in the rate between the two trials is due solely to the reactant whose concentration did change. So like we said that at first, we were looking at the one where H2 changed and ICL stayed the same. You have to have two trials in which one reactant is staying the same and another reactant is changing. Because if they're both changing, you don't know why the reaction rate is changing if it's from one reactant or the other. So you have to find one where one reactant is staying the same. Okay, number 2, by comparing that, You can determine the value of the exponent that's related to that reactant. So like with the H2, when we saw that it was doubled, the reaction rate also doubled. We knew that our exponent there was 1. So that's how you determine that. And then finally, after you determine the exponents, you determine the value for K by using the data from any trial, plugging it in and solving for K, just like we did. So that's just kind of a brief overview of what we did in the example. We're going to do another example, example 14.3 on page 502. A chemist studies the following reaction. 2NO plus Cl2 produces 2NoCl. To determine the rate equation, he runs the reaction 3 different times and comes up with the following data. Very similar looking table there for you. What is the reaction? What is the rate equation for this reaction? So once again, we're going to write our rate equation with what we already know. I'm going to share the screen, so hopefully that will be helpful. All right, so what we already know, let's clear this out since we have a new one. What we already know is that R is going to equal K. We don't have K yet. The concentration of NO to the X power, I'm just going to have to put X because I can't do exponents on here, but that X should be an exponent, times the concentration of our second reactant, which is Cl2, to the Y power. Again, Y is an exponent here. Okay, so now we need to solve for X, Y, and K. So first we're going to figure out our exponents. So let's look at our data. We need to find 2 trials in which one reactant stays the same and one is changed. So let's look at trials 1 versus 2. In trials 1 versus 2, you'll notice that the concentration of Cl2 stays 0.5 in both trials. But the concentration of NO is doubled. It goes from 0.5 to 1 molarity in the second trial. So anything that happens to the reaction rate is going to be based on that NO. So we're solving for X right here, okay? So let's see. Let's see what happens. R equals K. Concentration of NO. And the reaction rate went from 0.019 to 0.076. Okay, well, that tells me that, let's see, we're going to divide to see how many times that went up. So 0.076 divided by 0.019. So it increased by a factor of 4. So that means when concentration is doubled, the reaction rate is increasing by a factor of 4. So what we need to do is figure out what exponent is going to give us that 4 factor. So let me say it the way they said it because they said it best. The NO concentration increased by a factor of 2, but R increased by a factor of 4. So what do we need to do to turn a factor of 2 into a factor of 4? We need to square it because 2 squared equals 4. So that means our X, our exponent there for NO, is 2. Hopefully that makes sense. All right, now we need to find a reaction or the 2 trials in which the concentration of Cl2 changes, but the concentration of NO stays the same. So I'm looking at trials 2 and 3. NO is staying 1 molarity for both of those trials, but Cl2 is doubling from 0.5 to 1. So the reaction rate went from 0.076 to 0.152. If you need to, you can go ahead and divide that again. It's 0.152 divided by 0.076 to tell you. And it looks like that doubled as well. So because when you double the concentration, the reaction rate doubles. Again, they're linearly proportional. So that means X or Y is just going to be 1. So Cl2. We don't need to put the 1 because anything to the first power is the same. All right, so now that we have the exponents, now we can solve for K like we did before. So what we're going to do is choose any of the trials to plug into our rate equation that we have here and solve for K. So it looks like they are going to use trial 1. So let's plug in R, which is 0.019. molarity per second equals K times the concentration of NO is 0.5. Let's do 0.50. And that is squared. I'm sorry that the 2 cannot be an exponent in this app, but that is definitely squared. And then that times the concentration of Cl2. Okay, so what we need to do, just like we did before, oh, and these are molarity, I apologize. What we need to do, like we did before, is divide by this times this so that it will cancel, and then do the same thing on this side. So what you're going to end up with is 0.019 molarity per second divided by 0.50 molarity squared times 0.50 molarity equals K. So I just moved these to the other side, and now I have K by itself. We're going to plug that in the calculator. When you do, don't forget that your unit here is also going to be squared. So that is going to leave you with 0.15, 1 over molarity squared times seconds. This should be an exponent, that's m squared times seconds. And that's because you're left with 2 molarities in the denominator this time, not just 1. Okay, so this is going to be your K value for your rate equation, always for this chemical reaction. All right, so now that we know that, let's see. Oh, they did want to point out here that the units for K, the rate constant, can vary depending on the exponents of the rate equation. So like we had before, 1 over m times s, this time is 1 over m squared times s. So it can change based on the equation that you're doing. So it's going to be based on the exponents that are used. Alrighty, so now that we have that, that's all they asked me for. Well, I need to rewrite it in the equation. So R equals, plug your K in, and don't forget your units. Concentration of NO squared, this should be an exponent, concentration of Cl2. And that would be your rate equation for any concentrations of these 2 reactants. Hope that makes sense to you guys. I know it's a lot. All right, we've got one more example. It says, I'm on page 504 in black, the bold black writing. To determine the rate equation for the following reaction, a chemist performs a rate study and gets the following results. What is the rate equation for this reaction? Okay, we're going to do the exact same thing again. All right. So for right now, let's write out what we know. R equals K times the concentration of our first reactant, which is C4H9Br. Okay, to the X power, times our concentration of our second reactant, OH negative, to the Y power. All right, this is what we know so far. Now, let's look and see if we can figure out our exponents. So we're looking for 1 trial or 2 trials in which 1 concentration stays the same and 1 changes. So I'm going to look at 1 and 2. So in 1 and 2, the concentration of OH is staying the same, but the concentration of my first reactant is doubling. Okay, so let's see what happened to the reaction rate. It looks like it went from 0.0010 to 0.0020, so it doubled as well. And that was for C4H9Br. So that tells me that the exponent for that reactant is just going to be 1. Okay, now I know X, so let's work on Y. All right, so Y, we need to look at, looks like trial 1 and 3, because in 1 and 3, you'll notice C4H9Br are both 10. They're staying the same, but OH is going from 0.1 to 0.2. So let's see what happened to the reaction rate there. Well, it went from 0.0010 to 0.0010. So actually nothing happened, which tells me that the concentration of OH has no effect on the reaction rate, which means I can actually put Y as an exponent of 0 because it has no effect. So anything raised to the 0 power is just 1. So that means I can actually take this out completely because it's not going to affect the rate equation in any way because it's just going to be 1. So it's just extra work we don't need to do. So now this is what our rate equation looks like. Now I just need to solve for K. So what we're going to do is, like we did before, plug in the values for any trial. Let's use the first trial because that's what they did. So R there is 0.0010 molarity per second equals K times the concentration of C4H9Br, which is 0.10 molarity. Now this is pretty easy. To get this K by itself, I'm going to divide by 0.010 molarity and do the same thing on this side, which is going to leave me with the reaction rate divided by 0.10 molarity, and that's what K equals. So once you put that in your calculator, you see the molarity here and the molarity here canceled. So this will be an interesting unit. You're going to get 0.010, and your unit is going to be 1/seconds because both molarities canceled. And that's what K equals. So now to rewrite our rate equation for this chemical reaction, R equals, I'm going to plug in K that I just found. Don't forget your units. Times the concentration of C4H9Br. And that is it. Okay, we're going to do 14.3 and 14.4 for you. One thing that they did want to just emphasize before that is we know we said yesterday that it's true if you increase the concentration of a reactant that it's going to increase the rate of reaction, but it's not necessarily true for all the reactants. As we clearly see here, the concentration of OH was not affecting the reaction rate at all. So sometimes the rate of a chemical reaction will be unaffected by the concentration of one of its reactants. And in this case, the exponent of the rate equation is 0 for that reactant, just like we did here. That's in blue there on page 505. All right, now we're going to do 14.3 and 14.4, and that will be the end of class today. Hopefully I have time to do them. If not, that's okay. And we'll hit the highlights of the rest of the module tomorrow. All right, so student book 14.3. All right, let's start with what we know. Let's read it together. A chemist does a rate analysis on the following chemical reaction. H2 plus 2NO produces N2O plus H2O. He comes up with the following data. There's your table. What is the rate equation for this reaction? All right, like we did before, we're going to write out what we already know. R equals K times the concentration of my first reactant to the X power, that's an exponent there, times the concentration of my second reactant to the Y power. This is what we know so far. Let's try to figure out what the exponents are. So let's look at trial 1 and 2. H2 is staying the same, but NO is doubling, okay? So this is going to tell us why, because we're looking at NO. So what happened? The reaction rate, I'm going to divide 0.02268 divided by 0.005670, because I'm dividing my final rate by my initial rate. And I get 4. So it looks like when we double the concentration of NO, our reaction rate increases by a factor of 4. So that means Y is going to be 2. Remember, like we talked about before, because you're doubling NO, how do you get from 2 to 4? You square it. So let's just plug in what we know. And this is NO, the concentration of NO squared. Okay, let's figure out H2. Let's figure out the exponent X for H2. So it looks like we are going to do trials 2 and 3 for that one, because that's the 2 where the concentration of NO is staying the same. And we are actually tripling the concentration of H2. So when we triple it from 0.7 to 2.1, let's see what happens to the rate. So we divide our final one, which is 0.06804, divided by our starting rate, 0.2268, and we get 3. So when we triple the concentration, the reaction rate also tripled, which means X is just going to be 1 in this case. Okay, so now we have the reaction rate is equal to K times the concentration of H2 times the concentration of NO squared. Now we're going to do what we did before and plug in the information for any of the trials. So it looks like I used the second trial whenever I did it, so I'm just going to go ahead and use that one again, but you can use any trial that you want, trial 1, 2, or 3. So we're going to plug R in, which is 0.02268 equals K times the concentration of H2, which is 0.7 in this trial, times the concentration of NO, which is 0.6, and that's squared. All right, to get K by itself, I'm going to divide by, remember this is multiplying, I'm going to divide by 0.7 times 0.6 squared, and I'm also going to do it on that side so that K is by itself. I forgot my unit for rate, so I'm going to plug that in now. Molarity per second divided by, and that's going to be 0.7, and that's molarity, times 0.60 molarity squared. And once we, and all that, sorry, is equal to K. And once we plug that in the calculator, don't forget to put your whole denominator in parentheses. Let's just go ahead and do that. Hopefully that will be helpful to you. Okay, so we want this number divided by this whole thing, 0.7 times 0.6 squared. Once we do that, we're going to get 0.09. And if you'll notice here, I have 1 molarity in the numerator, so that's going to cancel with this one. And then I'm going to be left with seconds in the denominator and molarity squared in the denominator. So my unit, 1 over molarity squared times seconds. And that's what K equals for any concentrations for this reaction. Okay, so now we're just going to rewrite the equation for what we know. So R equals, I'm going to plug K in, which I just found, times the concentration of H2, whoops, times the concentration of NO squared. So really, once I find K, I'm going back to this step here and filling in K to write my rate equation. Okay? And that would be your rate equation for 14.3. Let's work on 14.4. Ozone can be destroyed by certain pollutants, one being the nitrogen dioxide that is expelled from the exhaust of cars and planes. The reaction that governs this process is NO2 plus O3 produces NO3 plus O2. A chemist does the following experiment to determine how fast this ozone destruction occurs. And there's his data. All right, so they're asking again, what is the rate equation for this reaction? So let's write what we do know is that R equals K times the concentration of my first reactant, NO2, to the X power times the concentration of my second reactant, which is O3, and that's to the Y power. Now we need to figure out X and Y. So R is going to equal K times the concentration of NO2. Let's look and see if we can figure out X. So I'm looking to see a trial in which the concentration of NO2 is changing and the concentration of O3 is staying the same. So I'm going to look at trials 2 and 3, because in 2 and 3, the concentration of NO2 is doubling and the concentration of O2 is staying the same. Let's look at what happened to the rate. It looks like the rate doubled as well. So that means X is just going to be 1, because when you double the concentration, the rate also doubles. So exponent is just 1 here. Next, let's do the value for Y. So I'm looking for 2 trials here in which NO2 is staying the same, but O3 is changing. So I'm looking at trials 1 and 3. NO2 stays the same, O3 is doubled. Let's see what happens to the reaction rate. Well, the reaction rate stayed the same, 0.088 and 0.088. So remember, like we said before, this means that O3 is not having any effect on the rate, which means the exponent is 0, which means I can just take it out because the value is just going to be 1. So the reaction rate is equal to K times the concentration of NO2. Now I'm going to plug in the values for any of the trials. So I'm going to use trial 1. All right, so let's plug in R, which is 0.088 molarity per second equals K times the concentration of NO2, which is 0.000100 molarity. Okay, now to get K by itself, I'm just going to divide by, sorry, this is multiplying. I'm just going to divide by this number, and I'm going to do the same thing on this side to get K by itself. So 0.088 molarity per second divided by 0.000100 molarity equals K. You're going to plug it in your calculator. When you do, you're going to get 880. Is that right? I might need to try that just to double check, because that sounds weird to me. Where's my calculator? Oh, there it is. Okay. So 0.088 divided by, you got to watch your zeros in this one, 0.0001. Yep, 880. So 880, and our unit is going to be 1 over, I had 1 molarity on top and 1 on bottom, so that canceled. So all that's left on the bottom is seconds, and that's going to equal K. So now remember, I'm just taking my K value and I'm plugging it into this equation right here that I already know. So this will be the rate equation for this chemical reaction. So R equals 880, 1 over S times the concentration of NO2 for any given concentration. And that would be your rate equation. All right, I hope that made sense. I hope you come back and watch this. I know it was a little bit of a weird equation, so if you have questions, let me know. And tomorrow I'm gonna just give you the highlights of the rest of the module and send you home with a practice final exam. Hope y'all have a great day and hope to see you tomorrow. Bye.